Welcome back, class. Today we are going to continue our discussions on kinetics and talk about the idea of catalyst and catalysis. So throughout the course of our discussion of kinetics, we've talked about different topics or different ideas that will affect the rate of reactions, right? We talked about how the concentration can affect the rate of a reaction. We talked about how temperature can affect the rate of the reaction, right? And remember, temperature will change the rate constant, right, of the reaction. Now, another way that we can change the rate of the reaction is to use what's called a catalyst. So, by definition, catalysts are simply substances that affect the rate of the reaction without being consumed. Now, for the most part, we think about catalysts as being things that speed up a reaction. Now, technically there are, quote, catalysts, typically called inhibitors, that actually slow down the rate of the reaction. Sometimes you want to do that. But for the most part, when people talk about catalysis, we're talking about ways that we speed up a slow reaction. Now, unlike concentration and temperature, catalysts work in a little different way. So earlier we talked about the idea of an activation energy for a reaction, right? That a reaction has a hill it has to overcome in order to go from reactants to products. Now what catalysts do is they provide an alternative mechanism. So they actually change the mechanism that the reaction operates by, and they provide an alternative mechanism that has a lower activation energy. So catalysts speed up a reaction by lowering the activation energy by changing the mechanism that the reaction occurs by. Now, we also say that a catalyst isn't consumed. And what we mean by that is that it's used up or used in one step of a mechanism, right? And then regenerated in a later step or released in a later step. So it isn't used up in the process. So that means, a small amount of catalyst can function in a lot of reaction, right? Because it can be used over and over and over again because it's not consumed. So we can look at several examples. So I'm going to first of all talk about the example that the book talks about most, which is the breakdown of ozone, specifically in the atmosphere. So without any kind of catalyst, this is an extremely slow process, right? And this is why, the ozone levels in the atmosphere stayed relatively constant, right? Because while ozone can break down into oxygen gas, right, combining this mechanism here, right, it's a very slow process. Right? Now, if a catalyst is provided, and the catalyst that we believe is responsible for breaking down ozone in the atmosphere, which is chlorine, Cl, right? So if we compare these two mechanisms, looking at their energy diagrams, we see the following. So that initial mechanism with one step that's relatively slow is shown here in blue, right? It has a very high activation energy to get around to our products, right? Now, if we look at the catalyzed pathway with chlorine, we see that there are two steps and each having lower activation energies than the uncatalyzed, and even put together, they have a lower activation. So what we get is a lower activation barrier, which is of course going to lead to more molecules having enough energy to get over the barrier, therefore more productive collisions, therefore faster reaction rate. And so this is how the catalyst is functioning, right? So the chlorine is being used in the first step, and then notice when we looked at that mechanism, it's used here, then regenerated here, or released here. So again, then this can go back and be used again. So, and this is why we don't need a lot of catalyst, because it's involved in the reaction, but not consumed by the reaction. Now, when we talk about catalysis, there are two types of catalysis. There are heterogeneous and homogeneous catalysis. So, in heterogeneous catalyst, the catalyst is in a different phase than the reactant molecules. So, for example, the catalyst might be a solid, the reactants might be a gas or in solution. Now, typically, these heterogeneous catalysts work by holding a reactant molecule in a proper orientation. So most of the time what we see here is that we have a solid state catalyst and the reactant molecules attach to that catalyst. So they become bound to that catalyst and it holds them in the right orientation. Remember, that's one of the things that slows down a reaction. Right? And so when the collision occurs with some other reactant molecule that's flowing by or in solution, then you get higher reaction rates because the one reactant is already in the proper orientation. Okay? So now, that's not how all heterogeneous catalysts have to work, but this is, a common way that a heterogeneous catalyst would work. So the key here is the catalyst is in a different phase than the reactant particles. Now, homogeneous catalysis is just the opposite, right? Everything is in the same phase, right? Everything is either in solution, everything is a gas, etc. So everything is in the same phase. So oftentimes here, right, the catalyst will react with a reactant molecule to form a more stable activated complex, right, which allows the reaction to proceed with a lower activation energy. Right? Okay. So we got heterogeneous, homogeneous catalysis. So you need some pictorial ideas, right? So this would be homogeneous, right? Everything is in the same phase. We have a product, we have a reactant, we have our catalyst, right, in the same phase. Here we have heterogeneous, right? Our catalyst is down here, typically like a solid in a different phase. We have our reactant and product molecules up here in gas phase, solution phase, etc. So different phases, same phase. So let's just close this out by talking about some examples. So let's talk heterogeneous. Well, it's believed that when we talk about the depletion of the ozone, that's actually occurring by a heterogeneous process. Now, the mechanism that I showed doesn't initially indicate that, right? But one of the pieces of evidence that helped determine that we think that there's some sort of heterogeneous process is that it's cyclical by seasons, right? And we can see the ozone hole, right? The depletion of the ozone shown here, right, is bigger in the winter months, in the fall and winter, in the cold months. Right? So the idea is that the chlorine gets holds on or gets attached to tiny ice crystals in the atmosphere that provides the catalyst, right? And then the ozone can then more thoroughly, interact with this supported catalysis of involving these tiny ice crystals. And so the chlorine, and I'm simplifying it a bit. There's a bit more discussion in the book, and it's not necessarily go into all the details here, but the chlorine, the actual catalyst, is being held in a heterogeneous fashion in these ice crystals, allowing the ozone depletion to occur at a more rapid rate during these cold winter months where these ice crystals are present. Right? As it warms up, the ice crystals are no longer there, and this same heterogeneous process can occur, and we see a lowering of the ozone hole, or a slowdown of the ozone depletion. Okay. So just one example of heterogeneous. Other common examples or places where we see heterogeneous catalysis is in industry, right? A lot of industrial processes that we've heard of operate by a catalyst. So, for example, the Haber process to make ammonia operates by a heterogeneous iron catalyst is involved. So that's to speed up the reaction. We'll talk more about the Haber process in a later chapter when we talk about equilibrium as an example there. But, this is a relatively slow process, the reaction between nitrogen and hydrogen, right? But the presence of this heterogeneous iron catalyst helps speed up this process. So, Haber process, this is another example. Other industrial processes are shown here. This is hydrogenation, the conversion of ethene, right, which has a double bond. So this would be H2C double bonded, right? So it looks like that. So we're hydrogenating, right? Adding hydrogen, and we're producing, it doesn't say here, but this is CH3, ethane. So we've added hydrogen across that double bond, turning it into a single bond, right? This is a heterogeneous process, this hydrogenation, right? Again, one of the processes used in certain industrial processes. Now, another really important example of a heterogeneous catalysis is the catalytic converters in our cars. So all cars are fitted with these catalytic converters, and they convert harmful molecules that are produced during the combustion process. So via incomplete combustion, typically, we get carbon monoxide, we get hydrocarbons that are not combusted in the engine, we get production of nitrogen O2 compounds because of impurities present in fuels, etc. But the catalyst that are involved in our catalytic converter, and just by simple example, catalytic converter, and I will have a video that has a little bit more detail here, is ceramic, but on top of the ceramic is where the catalysts are actually supported, and these catalysts typically involved fairly rare, expensive metals, platinum, palladium, rhodium, and this is one of the reasons why catalytic converters are not cheap, right? We use some of these quite expensive metals, but on the other hand, right, we use relatively small amounts of them, and they last for a long, long time, and they're very efficient, right? We reduce to almost nothing the amount of CO and hydrocarbons and NO2 that come out, and these are converted into nitrogen gas, water, carbon dioxide, things that are not harmful to the environment. So catalytic converters have, been extremely important in reducing air pollution, and they operate via this heterogeneous catalysis process. So that's some examples of heterogeneous. Let's look at homogeneous. So homogeneous, again, really important in industrial processes. Just to name a couple, we have polymerization, production of widely used polymers, or you might refer to plastics, like polypropylene or polyethylene, right? PE, and I'm sure you've seen the symbols PP or PE on plastics, right? These are polyethylene, polypropylene, and a lot of these are produced via a homogeneous process, right? using molecules, which are sometimes called Ziegler-Natta catalyst or metallocene catalyst, to do this process, right? And this is done in solution. Now, just as a side note, right, there is a sort of a reason why I chose this particular example, right? Molecules like this are what I did my research on in graduate school, wrote my thesis, right? And these are molecules like this have become more and more important in the production of these, widely used polymers. Now, another really important, industrial process that maybe we've never heard about is what's called the Monsanto's acetic acid process, which is one of the ways that acetic acid is produced industrially, utilizes another metal catalyst, and is done, again, in a homogeneous process. And we can see here, ultimately, the production of acetic acid. Okay, so again, a couple examples of where we see homogeneous catalysis in sort of our normal world. Now, I've saved sort of the most important homogeneous catalysis for last, and that is homogeneous catalysis that occurs in our bodies and in other plants and animals via the use of enzymes. Enzymes are simply biological catalysts. And of course, they function homogeneously because everything is in solution. So one thing I want to get some confusion, right? All homogeneous versus heterogeneous is the phase that things are in. It doesn't mean that things don't attach to things and make it, make a more active site. We sometimes consider that to involve heterogeneous, where one molecule gets absorbed onto one and the other one reacts to it. This can happen in homogeneous catalysis as well, where a molecule connects to another one and that aids in the process by changing the orientation of that molecule, etc. Right? The key is everything is in the same phase versus different phases. Right? So enzymes, which I'm sure a lot of you have heard of, again, are simply catalysts that occur in biological systems. But a lot of biological processes, like cellular respiration, like the breakdown of large biomolecules, right, occur at very slow rates if they were to be uncatalyzed or not at all, or would require high temperatures to occur, right? And of course, the body doesn't have those sort of things available to it. And so catalysts are necessary to change or to raise the rates of these, what would be slow processes, to, necessary rates, right, that are necessary, to maintain a living organism. Now, enzymes are proteins, and they catalyze mostly by doing what like I'm saying, they absorb the substrate, right, which is one of the reactants, into what we call the active site of the enzyme. And this active site orients, right, gives the molecule the correct orientation to get a productive reaction, to get a productive collision. And then when the other molecule comes in, or perhaps it's, just the single molecule, but it has to break down that molecule, right? It can happen at a faster pace. So you might have a process that looks something like this, where the enzyme combines with the substrate, right? So we get this complex. Then this complex goes back to regenerate the catalyst and produce the product, either by, allowing the substrate to break down into multiple molecules, or allowing it to be in the right orientation for another molecule to come and react, etc. So let's look at one example that we can use. Now, Now, there are many, many examples, right? There are hundreds and hundreds of enzymes out there. Well, probably many more than that, thousands, right? That do very specific tasks. And again, I'll have a video that maybe gets a little more detail into the enzymes to give you a little bit more perspective. And so this particular example is the breakdown of sucrose, the hydrolysis of sucrose into two sugars, right, into glucose and fructose. So breaking down this disaccharide, right, this larger sugar molecule that we consume, into monosaccharides, into smaller sugars, which our body can then use as energy. Now, to break down this bond, right, so the bond we have to break is right here, this carbon-oxygen bond. Right? Uncatalyzed, would be a hard process, right? A slow to break down that covalent bond. But when sucrose comes in and binds to the active site of our enzyme, sucrase, it strains this bond, right? It bonds in an orientation in the active site that puts stress on this bond, weakens it, and allows it to break more easily. And so the idea is the enzyme comes in, forms our complex, weakens this bond is allowed to break, and then the two sugars release from the active site. And then another molecule of sucrose would come in, and this would happen over and over and over again. So, enzymes. All right, so a little bit of discussion on catalysis, and again, to talk about catalyst works, by reducing the activation energy. And it's the only thing that actually changes the activation energy. So when we think about these different things that we've talked about in the chapter, we've talked about, the rate constant, the rate law, the activation energy, right? Remember, in general, the rate of the reaction, or the kinetics, right, is independent of concentration, right? So there is a rate law for the reaction, right? And we can change the concentration, right? The rate law is the same, right? We can speed up the process by raising the concentration, lowering the concentration based on the rate law. Now, but that rate law is the rate law, and that reaction has a rate constant. That is the rate constant. Now, the key thing to remember is that rate constant is specific to a given temperature, right? The thing that we can do to change the rate constant is to change the temperature. And so, typically for most reactions, raising the temperature will lower the rate constant, which allows the reaction to be faster, right? Lower rate changes the rate constant, allowing the reaction to be faster. Okay? So we can affect the rate constant by changing temperature. That's physically, that's mathematically what it does, right? It changes the rate constant. Now, we talk more detail in that specific section about how it does that. What the process is. What raising the temperature does, to allow the reaction to be faster. So you want a little more detail. But, even changing the temperature, right, we have this activation energy, right? And so basically changing the temperature is just helping push more molecules over the activation energy barrier. But catalysts do something different, right? They don't change, right, just the rate. They don't just change the rate constant. They change the rate law, right? They change the mechanism of the reaction, and they change it to a mechanism that has a reduced activation energy. So the way catalysts work is by lowering the activation energy. All right, so as we wrap up the chapter, I will direct your attention to some videos that I will also be posting on individual sections that look at some practice problems that I'm going to go through on specific topics. I will also be posting other supplemental videos and assigning those videos based on topics So remember to check out the weekly assignment sheet to know which videos are assigned for individual days.